Imagine looking up at the night sky, countless stars, galaxies, and nebulae, each a sun with its own worlds. All this vastness had a beginning, the Big Bang. The Big Bang theory describes how everything emerged from an incredibly hot, dense state nearly 13.8 billion years ago. It wasn't an explosion in space, but the expansion of space itself, the very beginning of space and time. Before the Big Bang, there was no before as we understand it. Time itself began with this event. The entire observable universe was once compressed into a space smaller than an atom. From that singular point, space began to stretch, carrying everything with it, and has been expanding ever since. This idea challenges our intuition. Space and time themselves were born in that moment. The Big Bang is the ultimate origin story, not just for our planet, but for the very rules of physics and the dimensions we move through. It connects the atoms in your body to the most distant galaxies, all born from the same ancient event. How did we arrive at this conclusion? It took a century of observation and deduction. Scientists like Einstein, Lemaitre, and Hubble pieced together clues from the light of distant galaxies and the faint afterglow of creation. Each piece of evidence pointed back to a single explosive origin. The Big Bang Theory is our best scientific explanation for these observations. It's a narrative woven from the very fabric of space-time. Let's journey back to the very first moments of our universe. The Planck epoch marks the earliest moment we can describe, lasting from time 0 to about 10 circumflex 43 seconds. The universe was unimaginably small, hot, and dense. The four fundamental forces were unified into a single superforce. The laws of physics as we know them didn't apply. Temperatures soared above 10 circumflex 32 degrees Celsius, where our current theories break down. To understand this era, we'd need a theory of quantum gravity, something scientists are still working on. Space and time were fuzzy, a churning quantum foam. Tiny quantum fluctuations in this foam would become the seeds for the universe's large-scale structure. As the universe expanded, these fluctuations were stretched to astronomical sizes. They became the seeds for stars, galaxies, and clusters. At the end of the Planck epoch, gravity separated from the other forces. This marked the end of the singularity's dominance and the start of a new phase. The universe was still bizarre, but the familiar laws of physics began to emerge. This set the stage for the next dramatic chapter: cosmic inflation. After the Planck epoch, the universe entered the inflationary epoch, a period of astonishingly rapid expansion. In a fraction of a second, the universe grew from smaller than a proton to the size of a grapefruit. This expansion was faster than light, but it was space itself expanding. Inflation solved key puzzles: the horizon problem, why the universe looks uniform everywhere, and the flatness problem, why space appears geometrically flat. By stretching a tiny connected patch to cosmic scales, inflation made the universe uniform and flat. The energy field driving inflation, called the inflaton, decayed at the end of this period. Its energy transformed into a hot, dense soup of particles and radiation, a process called reheating. The universe was now filled with quarks, leptons, and bosons. Forces continued to separate, and the building blocks of matter began to form. Inflation's end set the conditions for everything that followed. The universe was primed for the creation of matter as we know it. Next came the formation of the first particles. After inflation, the universe was a seething plasma of fundamental particles: quarks, electrons, positrons, and photons. Quarks, the building blocks of protons and neutrons, existed freely in a quark-gluon plasma. Particles and antiparticles formed and annihilated constantly, demonstrating Einstein's E=mc squared. As the universe expanded and cooled, quarks began binding together, forming the first protons and neutrons. This was a monumental step. Matter was assembling into stable structures. Yet matter and antimatter were nearly equal, except for a tiny surplus of matter. This slight asymmetry is a great mystery, but it allowed matter to survive after most pairs annihilated. The leftover matter became everything we see today. For a few minutes, the universe was a nuclear furnace. Protons and neutrons fused to form the first atomic nuclei, mostly hydrogen and helium, with traces of lithium. This process, called Big Bang nucleosynthesis, predicted about 75% hydrogen and 25% helium by mass. Observations of ancient stars and gas clouds confirm these predictions. This agreement is strong evidence for the Big Bang model. The universe was now ready for the next transformation. Soon, light itself would break free. For 380,000 years after the Big Bang, the universe was a hot, opaque fog, electrons and nuclei unbound, photons trapped in a cosmic pinball machine. As the universe cooled to about 3,000 degrees Celsius, electrons combined with nuclei to form neutral atoms, a process called recombination. Suddenly, photons could travel freely. The universe became transparent. The light released at this moment began its journey across the cosmos. Over billions of years, this light's wavelength stretched into the microwave range. Today, we detect it as the cosmic microwave background, or CMB, a faint, uniform glow filling the sky. The CMB is the afterglow of the Big Bang, the oldest light in the universe. Its discovery in 1965 by Penzias and Wilson was a landmark for cosmology. The CMB isn't perfectly uniform. Tiny temperature fluctuations reveal the seeds of cosmic structure. Satellites like COBE, WMAP and Planck have mapped these ripples in exquisite detail. These fluctuations trace back to quantum variations from the universe's earliest moments. They show where gravity would begin to pull matter together, forming galaxies and clusters. The CMB is a baby picture of the universe, revealing its age, composition, and fate. By studying it, we unlock secrets of our cosmic origins. The next great clue came from observing distant galaxies. Enter Hubble's law. In the 1920s, Edwin Hubble observed that distant galaxies' light was redshifted. They were moving away from us. The farther a galaxy, the faster it recedes, a relationship now known as Hubble's law. This was the first direct evidence for the expansion of the universe. It's not that galaxies are flying through space, but that space itself is stretching, carrying galaxies apart. Like raisins in rising dough, every galaxy sees others moving away. This expanding universe is a cornerstone of the Big Bang theory. If the universe is expanding now, it must have been smaller, denser, and hotter in the past. Hubble's discovery confirmed theoretical predictions by Friedmann and Lemaitre. Today we measure the expansion rate, the Hubble constant, to estimate the universe's age about 13.8 billion years. More recently, we've learned the expansion is accelerating, driven by mysterious dark energy. This discovery opened a new chapter in cosmology. The universe's story is still unfolding. But how did the Big Bang set the stage for stars and life? The Big Bang theory predicts the abundance of light elements, hydrogen, helium, and traces of lithium, created in the universe's first minutes. During Big Bang nucleosynthesis, the universe acted as a massive nuclear reactor, fusing protons and neutrons into light nuclei. The predicted mix about 75% hydrogen, 25% helium, and tiny amounts of deuterium and lithium. Observations of ancient stars and pristine gas clouds match these predictions exactly. This cosmic recipe is why we exist. Hydrogen and helium formed the first stars. Inside stars, nuclear fusion created heavier elements: carbon, oxygen, iron. When massive stars died as supernova, they scattered these elements across space. New stars and planets formed from this enriched material. The atoms in your body were forged in stars, from the raw materials of the Big Bang. The Big Bang theory is the leading model for the universe's origin, supported by overwhelming evidence. Its success comes from explaining a wide range of observations with accuracy and consistency. The three main pillars, the universe's expansion, the cosmic microwave background, and the abundance of light elements. The CMB's properties and the observed element ratios match predictions perfectly. The theory also explains the large-scale structure of the universe, the cosmic web of galaxies and voids. Computer simulations based on the Big Bang model reproduce this structure remarkably well. It even solves puzzles like why the night sky is dark, Olber's paradox. The Big Bang theory has survived decades of scrutiny and ever more precise tests. While mysteries remain, its core principles are robust. It's the foundation of modern cosmology. Despite its success, the Big Bang theory isn't complete. It describes what happened after the beginning, but not the beginning itself. What happened at time zero? What was before the Big Bang? Our laws of physics break down at the singularity. We need a theory of quantum gravity to answer these questions. The nature of dark matter and dark energy remains a profound mystery. Together, they make up 95% of the universe. The matter-antimatter asymmetry is another puzzle. Why did matter win out? And what is the universe's ultimate fate? Will it expand forever, freeze, rip apart, or collapse? These questions drive cosmology today. The Big Bang Theory gives us an incredible origin story, but the final chapters are still unwritten.